All right, let's get started. Good afternoon and welcome to the 24th annual and first virtual Children's Water Festival. I'm Rachel, your host and MC, and I want to thank you all for being here. I also would like to thank some of our sponsors, the City of Dayton Department of Water, Cargill, Hazen and Sawyer, LexisNexis, T&M Associates, Xylem Analytics, Miami Conservancy District, Pace Analytical Services, Woolpert, and Wood. Today, we're going to be using Zoom, and if you aren't familiar with some of the functions, this is what we will be using today. So your screen should look pretty similar to mine down at the bottom. You are welcome to utilize the Q&A function to ask questions of our presenters about any of the things they're discussing. Again, the chat is for teachers only. And then at the end of the presentation, you can hit that end button to leave. The presentation will be about an hour. And today we're going to be talking about aquifers and drinking water. Welcome back. Today we'll be learning about drinking water and aquifers. Hey Willie, welcome to the water treatment plant. This is where we clean the water so that it's safe to drink. Hey Willie, what are you doing? No, you can't swim in there. That's not a pool, it's a salad basin. It's a part of the water treatment process. Come on. Hey Willie, what are you doing? No, you can't build a sandcastle. That's not a sandbox. That's a filter. It cleans the water. Welcome to the lab, Willie. This is where we test the water to make sure it's safe to drink. We use chemicals to show us what's in the water. Hey, Willie. What are you doing? No, Willie. There's no water in there. It's only up in the bowl. Teachers, if you get a chance, take some photos of your students enjoying the festival experience. Now we're going to learn about aquifers from the City of Dayton Department of Environmental Science.
Hi everyone, my name is Paul Fleischman and I am going to talk about aquifers. Some of you already may know what aquifers are and some of you may not. Hopefully today we can learn a little bit about aquifers and why they're important to us. So like I said, I'm Paul Fleischman. I work for the City of Dayton Department of Water, the Division of Environmental Management, and I am an environmental compliance coordinator, which I focus mostly on source water protection, which is the water that we use for drinking water.
And I'm Eric Forth, and I'm also an environmental scientist in the Division of Environmental Management. So I focus a lot on data management and also just the general inspections and testing that we do to keep the aquifer safe. And I'd also like to introduce our division and what we do. The first thing is source water protection. This is what we'll be focusing on today. Our source water is the aquifer that's beneath our feet. So we'll be learning a lot more about aquifers throughout the presentation. But I also wanted to introduce a couple of other things that we do, like surface water protection, which you may have learned about yesterday. So we are the ones who go out and sample the water in the rivers, sample the water that's going into the rivers from all of our outfalls where the storm water drains. And we're making sure that those are safe and clean for all of us. And a lot of this also, we do emergency response. So any car accidents or fires or emergencies that will happen that may threaten our surface water or source water, we'll go out there to make sure it's cleaned up correctly. So the ambulance will go out to make sure all the people are safe, and then the fire truck might go out to make sure the fire is put out. But we will go out there to make sure anything that's leaked, any gasoline or any chemicals that might have been stored in a truck, that's cleaned up in a way that it's safe for our drinking water and our surface water. And then the last thing we do is outreach and education, which is a perfect example is what we're doing right now. So I know we all love to get out and talk to community members and students like yourselves to really talk about what we do and these resources and how important it is for us to protect them. And so circling back to aquifers, we have this video to really go into what an aquifer actually is.
We all know the Earth is full of water, but there's a lot more to water than all that blue stuff you see on the globe. The water we can see on the surface of the Earth is surface water. Surface water is every lake, pond, river, stream, and ocean on Earth. But in the ground below your feet, there's even more water, groundwater. Groundwater is water that's crammed in the tiny gaps between rocks, soils, and sediments under the ground. A full body of groundwater is called an aquifer. There are huge aquifers all across America. The biggest is the High Plains Aquifer, which covers 174,000 square miles right in the middle of the country. Anything that big deserves a closer look. Let's say you could grab a shovel and dig straight down through the soils to an aquifer. The level underground where you first hit groundwater is called the water table. Below the water table, the ground is completely soaked or saturated with water, which is why this area is called the saturated zone. The area above the water table is called the unsaturated zone. So how does all this water end up in the ground? Well, it's all a part of the good old water cycle. When it rains, some water gets soaked up by plants. Some water runs off the soil and into streams, lakes, or even the ocean. Other water gets stuck on the surface and eventually evaporates back into the air. Meanwhile, some of the lucky water droplets get to travel down through the surface deep underground until they reach the water table and become a part of an aquifer. Once water seeps down deep enough into the ground, it can stay there for a really long time. Some of the water stored in the deepest parts of aquifers has been there for thousands of years. But after it gets there, groundwater doesn't always stay in the ground. A lot of the water on the surface comes from aquifers. If the surface of the ground dips below the water table, groundwater flows out into the space, creating a body of surface water. If the surface water dries up, groundwater can flow in to fill it back up. And if the water table in this area rises, so does the level of the surface water. Groundwater can also pour down a sloping surface, creating streams. Any place where groundwater flows out into the surface is called a spring. Surface water can also become groundwater. If a body of surface water flows above the water table, water can seep down through the sediment and help fill the aquifer. Of course, there's another way that groundwater can leave the ground. Us. Humans depend on groundwater, and there are thousands of wells all over the country that draw water out of aquifers. In many parts of the country, the water you get from the tap comes from the ground. However, we use most of our groundwater to help grow the food we eat. Farms can get lots of the water they need from rain, but rain isn't always enough. And in dry years, farmers depend even more on the water that's stored in the ground. In fact, American farms use about 53 billion gallons of groundwater every day. That's enough to fill over 1 million bathtubs or 80,000 Olympic-sized swimming pools. So if we're using that much every day, can it run out? Well, yes and no. Remember, aquifers can be refilled by rainwater or surface water seeping in from rivers and streams, so there's usually more water on its way to replenish the aquifer. But if we use groundwater faster than the aquifers can refill, we could drain them dry. They probably wouldn't be empty forever, but it would take hundreds of years for the largest aquifers to get back to healthy levels. Whether it's up here or down there, water and how we use it matters. We may not be able to see it every day, but groundwater makes our lives possible. So don't let show-offs like rushing rivers and roaring oceans get all the attention. Those unseen aquifers below ground have been here longer than we have, and with a little love and care, they'll keep on taking care of us long into the future.
All right, so hopefully we were all able to learn a little bit more about aquifers and groundwater from that video. So now I want to just say that if you have any questions about any part of this presentation, go ahead and put them in the chat, and later we will answer them at the end of our presentation, okay? So what you're seeing now on the screen is a map of our well fields. This is the Dayton area, and actually on the bottom left side of the map, you can see downtown Dayton there. The blue parts of this map actually show our well fields that are right on top of the aquifer. And in fact, the one on the right-hand side, the Mad River well field, you may have seen some of our production wells there, because if you go into Eastwood Park, that's part of our well field. And if you see these big green pipes on concrete bases, that's a production well. And so that is pulling water directly from the aquifer and sending it to our treatment facility. Just to say a little bit more about this well field map. So because this, you can see these well fields are right where people live, right where businesses and factories are, we need to make sure that we do, like Eric had said, outreach and education. We check with people and businesses to make sure that they are handling their chemicals or anything else in the correct way to reduce risk to our aquifer. And we have that little zone of protection around there, the source water protection area. I'm going to show you here in a second. This program started back in the late 80s, and one of the reasons why it started, kind of gave us that bump to start it, was the Sherwin-Williams Fire. So you'll see now the picture of Sherwin-Williams, that plant, which had a ton of paint in it, was right next to the well field, and it caught fire. And so what happened was it caught fire, and it's right over our aquifer, right next to our well field where we are pumping drinking water. And the city decided, the firefighters in the city decided that they are not going to put water on that fire to put it out, because if they did, that water would have gone down through the soil down into the aquifer, and that would have been very bad for our well fields. It would have contaminated that water. So this is kind of one of the reasons we put in place this source water protection area and source water protection program. I'm going to go to the next slide here and explain one thing that, these well fields in the source water protection area, when the aquifer was formed and where water goes, they don't care, water doesn't care what city it's in when it's flowing. It doesn't care if it's in Dayton or Riverside or anywhere else. And so we, Dayton, partner with all of these other cities, Riverside, Harrison Township, Huber Heights, Vandalia, to protect our aquifer. And we do that by partnering with public health, Dayton and Montgomery County. So I am going to let Sarah, a partner from Dayton, Montgomery County Public Health, kind of talk a little bit more about her role with Source Water Protection Program.
Thanks, Paul. Hi, everyone. I hope you all are having a great time and are learning a lot. My name is Sarah, and I am a geologist. That's someone who studies the earth. I work for public health, and we are here to make sure the community, that means you, stay safe and healthy. That includes what we drink, right? So my position here at Public Health is Well Field Protection Specialist. That means I provide guidance to the 4 jurisdictions or areas that Paul just talked about outside the city of Dayton for anything they might need relating to our well fields. Maybe someone wants to know what chemicals are not allowed in the area, or where the nearest drinking water well is, or even if someone had an accident and the chemical was spilled on the ground outside. The 4 jurisdictions or areas that make up the Multi-Jurisdictional Source Water Protection Program are Huber Heights, Vandalia, Riverside, and Harrison Township. No matter where you live, each one touches a portion of the well fields. Also, I work with people who have businesses, factories within this area to make sure they know how important it is to be a great environmental steward. We are all partners because, like Paul said, water has no boundaries, but cities and towns and villages do, right? So, as you all just learned, the Source Water Protection Program is a large network of people that work together towards a common goal. And what do you think that common goal is? If you said to make sure the groundwater stays safe and clean to drink, you're right. Thanks for listening. Back to you, Eric.
Thank you, Sarah. That was fantastic. So we've talked about protecting the aquifer for a while, and we actually have a demonstration video here using our really cool model of the aquifer to show how contamination happens and spreads.
Hey everyone, so what we have in front of us here is a model of our aquifer. We say that because you can see what the aquifer is made of, the aquifer below Dayton. It is made of stuff like sand and gravel, clay here. And that's exactly like the aquifer that's underneath our feet where we are right now, the same aquifer where we get our drinking water. I have this model here to show you just a couple of the things that occur in the aquifer and kind of how water moves through. You'll see here we've got different wells, and these are basically just like the wells that are in our aquifer now. They're just tubes that go down into different parts of the aquifer. Some of those wells are monitoring wells where we check the water quality of the aquifer, and some of them are production wells, and that's where we get our drinking water. So other things that can be a part of the aquifer, especially up top, things that we can see, are rivers. You know, you see the grass here, you see the river here, kind of dumps below. And what that shows is that these have communication with each other. And so anything that could go into the river could possibly go down into our aquifer as well. So it can go through land, a river, or even things like storage tanks at gas stations or septic tanks. So what we're going to do today is I'm going to use this purple dye here, and I'm going to put it into this storage tank. And we're going to act like this storage tank is at a gas station, and they had some sort of leak that they did not catch. They did not know about it, and so all of a sudden they're leaking. And I'm going to use this well over here, this well number 5, and I'm going to turn on a pump. So what this pump will do is start pumping water out of the aquifer into this tube here, and you'll see that it will start pulling water from this entire area, and especially this fake contamination that we're going to put in this storage tank from the gas station. Okay, so I'm going to go ahead and fill up this storage tank here with our purple dye. We're going to call that gasoline at the gas station. And then you can see that it's leaking and that it's starting to come through already. That's not good. And then I'm going to turn on pump number 5 here, okay? So we can see that our fake gasoline here is starting to migrate over through the aquifer, comes from the storage tank, and is starting to come over to our pump number 5. See that it's migrating over. And as we continue to kind of release that gasoline from the storage tank, it keeps moving over towards this pump and pulling it up out of the aquifer, pulling water out of the aquifer. And I think it's reaching it now. So it's gone down through all the sand and the gravel, and now we are pulling up this red, purpley red water. All right, so as you can see with that demonstration, it is very important for us to have our program, the Source Water Protection Program, to be able to monitor groundwater quality and kind of make sure that those contamination issues don't happen. So we've learned a lot about our aquifer here in the Dayton area. We've learned that it's made from sand and gravel, and we learned that the water, rainwater and water from rivers, you know, gets in between those particles of sand and gravel. That's the aquifer, and that's where we pump our water for drinking. One thing that you can do, and you can see on the slide that I'm sharing right now, some of the teachers do have some of these materials. And if you don't have these materials to build your own aquifer, you can find them easily at home. So the materials are sand, gravel. I'm using a 2-liter bottle cut in half. And it's a pretty simple experiment to just kind of see how, you know, what an aquifer is and how it works. So I'm going to switch to my screen so you can see this a little bit better. And I'm going to be putting in sand and gravel. And I'm going to start with the sand, but you can do this a few different ways. You know, you could, if you wanted to, you could start with the gravel, and the sand will probably fill up the spaces in between the gravel. So I've got my sand down here, and then I'm going to put my gravel on top of there. And then lastly, I'm going to put, just like we have under our feet, dirt, where the grass is and everything else. So one thing I want you to think of while you are making your own little aquifer model is what would happen if, say, you were to fill this all with gravel? How much water could you hold in there? If you filled it all with sand, etc. So, you know, think about those questions and kind of form an answer before you start your little experiment. Anyway, I hope you take a chance to do this and kind of have your own little aquifer model. We're going to switch back to sharing now, and Eric is going to take over. All right.
Thank you, Paul. So the next thing I want to say is that we want you to help us protect this valuable resource. Like we all have the power and really the responsibility to keep this water safe. It's what we all drink. It's what we brush our teeth with. It's what we shower in. So it's really important. And if you see anything that looks like illegal dumping, so this is like when people will leave paint cans. I have some pictures down here, some paint cans left out on the street, or a bunch of tires or something like that. When the rain falls on that, that's going to wash those chemicals into the rivers or into the aquifer. So if you see anything like that, please ask an adult to call us. We want to get there and check it out and make sure everything is safe and clean for everyone. So just in conclusion, the groundwater is important, and it's up to all of us to help protect the drinking water. And with that, we will take any questions. And I'll stop sharing here.
Okay, one student wanted to know in regards to the aquifer model, Was the dye leaking because it wasn't good, or what was, can you explain a little more about what was going on there?
Sure, yeah. So for that model, that tank is supposed to leak. You know, it's just supposed to be able to show kind of that communication between, if you have a leaking tank or something on the surface, that, you know, contamination can come down into the aquifer, get into the aquifer, and then when you go to pull water, it can pull that contamination towards that production well.
Why is the ground made of sand, gravel, and clay?
That's a great question. So in this area, in the Dayton area, you know, like more than 10,000 years ago, it was covered with ice. So in the last glacial period, this area, and the way that the Great Miami Buried Valley Aquifer was formed is that those glaciers, you know, from up north, they grabbed sand and gravel and everything else as they were kind of moving across the surface. And when they got here and started to melt, that sand and gravel started to come out of those glaciers. And so what our aquifer is essentially made of, it was a valley before, and then that was filled up with sand and gravel. So that's why our aquifer is made of sand and gravel. Other aquifers aren't. There are different types, but that here in the Dayton area, it's a sand and gravel aquifer.
Awesome. If bad things spill in the water, will we run out of water to drink?
So there is a lot of water. The issue would be we would have to move our wells somewhere, which is very expensive. So we have a lot of wells on that map we showed with the well field areas. If something really bad did happen and one of those got contaminated to the point where we couldn't do anything about it, which there are techniques that we can use to help out, but if we can't, then we might have to move that, and that would be very, very expensive.
How does the water get underground?
Well, if you think back to that video, so it's hard to kind of think of, but when rain comes down, it doesn't just only go to a river or only go to the, you know, storm sewer on the street. It can get down into the grass, go below the grass, go down through the dirt. And if you remember from that video, there was a zone called a saturated zone. And so basically, as that rainwater moves down through and hits that saturated zone, that's how that happens. So it's slow, it's not quick, but it just moves through in between all the cracks and areas between the rocks and sand.
So that zone is kind of like a sponge. It's solid, but it still holds water.
Right, right. And if you try the model that with the sand and gravel, you'll see that. And some areas hold more than others.
How long does it usually take to clean out contaminated water?
Nothing at all about groundwater is fast. So I just said that, you know, the rainwater going down into the aquifer isn't fast. If there is contamination in an area of the aquifer, number one, it doesn't move that fast normally. So that's good. But again, then while we are trying to remediate that in some sort of way, pull it back out, it also doesn't go very quickly. It can be decades to fully clean up a contamination issue.
Okay, we have time for one more question live, and then I will answer the rest of the questions in the chat. Can an aquifer ever overflow?
Yeah, so that's a good question. When an aquifer overflows, what that would be is like a spring or something where you see water coming out of the ground. So that is that water table rising up and rising up, because if there's a lot of rain and it is that like some amount trickles down into that aquifer, it does start to fill and raise that water table. And that overflowing is kind of shows up as a spring coming out of the ground somewhere, or maybe just the water level of the river rising. So in a sense, yes.
Thank you so much, Paul, Eric, and Sarah. We learned a lot about aquifers. Now we're going to hear from Brandon and Emily with the City of Dayton Water Supply and Treatment.
All right, hello everyone.
Hello, good afternoon. My name is Brandon with the City of Dayton Water Supply and Treatment Division. I'm the Water Treatment Technical technical supervisor, and kind of a short version of what that means is I supervise the lab, and I'm over water quality in the City of Dayton's drinking water.
And my name is Emily Denlinger. I am a water instrumentation specialist, which is just a fancy way of saying I test the drinking water. So we go out to the plants every day, we collect samples and bring them back to the lab. And in my job, we test things like the wet chemistry, looking at like the hardness, the alkalinity, the pH of the water. We check for bacteria, which we'll get a little bit of a look at later. And instrumentation, specifically, we look at things like metals, total organic compounds, sulfates, nitrites, nitrates, things like that. After the water has been treated, that way we can make sure it's safe when it reaches people's homes.
So today we're going to kind of talk about the water treatment process and show you a few little experiments related to that. First things first, we have two drinking water plants. Both have the capacity of 96 million gallons a day each, and we use that water to send water to the City of Dayton and most of Montgomery County. So if you live in Kettering, Centerville, Washington Township, Trotwood, who else? No, not Huber. Anyways, most of the county we supply with drinking water. So if you live in those areas, that's City of Dayton water. Like I said, we have two plants. Both have the capacity to produce 96 million gallons a day, which is a lot of water. We typically don't produce that much. Typically, each plant probably produces about 90 million gallons a day combined. Both plants use what is called coagulation, flocculation, sedimentation, filtration. Basically, that means we add quicklime to the water, calcium oxide, and that quicklime kind of forms a chemical reaction, causes the particles to clump up and settle out. So coagulation is adding the quicklime, flocculation is the mixing of that quicklime, sedimentation is all those particles settling out. And then we filter the water like you saw with Willie Water in the video. She said, it's not a sandbox, Willie. That's our filtration system. And then we disinfect the water with chlorine and add fluoride for your teeth. Kind of bouncing off what environmental said, we pull our water from the ground, from the aquifer, and we recharge that aquifer with surface water. So that puts us in a groundwater under the influence of surface water designation. That means we have to monitor for a lot more things than just a straight up groundwater plant would have to. So we have to monitor for things like turbidity, cryptosporidium giardia, things like that. And cryptosporidium giardia are things like if you ever go hiking or camping, they tell you not to just go to a surface water, or river, or creek, stream, anything like that. They tell you not to just go up and just take a swig of creek water because it'll make you really sick. And what makes you sick is cryptosporidium giardia. Those are basically organisms that get inside your body and basically make you feel really bad. So that's one reason why. One of the things we're going to show you is this treatment system we have from Procter & Gamble that kind of helps prevent anything like that for basically water that if you don't have access to drinking water. Other than that, we have multiple tanks and reservoirs in the system. If you drive around the city or the county, you'll see, large water towers. You usually don't see the reservoirs. They're underground. You really don't know that they're there. But the reason for the water towers above ground is to create pressure in the system and also have some storage on hand of water. So we don't want to just always pump the water straight from the plant to your house. We like to have a little bit of backup. So that's what those storage facilities are for. I think that's it. I'm going to let Emily talk about her. Basically, this is like a mini water treatment plant that she's going to show you guys.
Yeah, so like Brandon was saying, we are going to do a little demo here of basically what happens at our treatment plant. So we have some dirty water here. Just a quick poll, would anybody drink this water? Probably not. I hope not. You shouldn't drink water if it looks like this. So what we're going to use, we have these packets. They're created by P&G. You can buy them from the website. You can buy them on Amazon. This isn't what we use over at our treatment plant, but this is just, again, a demo for a small scale experiment. But Procter & Gamble actually came up with these. They're made to treat up to 2.5 gallons of water, but initially they created them to take laundry water that was dirty and be able to convert it to safe, clean drinking water. Because in a lot of places, people don't have access to drinking water like we do. We can go to our tap in our kitchen or our bathroom sink, turn it on, and then we have a nice, clean, safe glass of water to drink. That's not the case everywhere. So they created these for countries that don't have that, or if you're in an emergency or you're out hiking, this would be great for that. So it uses the calcium hypochlorite. That's what's going to disinfect the water, kill any bacteria. And it also acts as a coagulant, like Brandon said. So it'll start this chemical reaction. The molecules will get sticky. And as we're stirring it, which is the flocculation, they'll start to get closer and closer, almost snowball, and then they'll get heavy enough to where they fall out of suspension. So that's what we are going to do here. Okay.
So that's the coagulation portion, adding of chemicals.
You can't see it, but it's fizzing a little bit. The chemical reaction is happening. Now with this, it has to be stirred for 5 minutes. So Brandon's going to do that. And I'm going to demonstrate a few other things that we look at in the lab. The first I'm going to show you is how we look at chlorine. So why is chlorine important? Think to yourself for just a few seconds. Think about a swimming pool, right? You want chlorine because it's going to kill any bacteria or viruses. So it's important that we have that in our drinking water. So every day we check the chlorine at the plants, and we also have samplers whose job is to go out in the distribution system. And the distribution system is anything outside the treatment plant. So that's neighborhoods, that's anything outside of our treatment plants, the distribution field. So if you're ever out driving throughout the city or the county and you see these tall green boxes on the side of the road, those are likely a sample station where they'll go and they'll collect water samples for us to test back here at the lab. And one of the tests that we'll do is to check for chlorine. So they fill this vial with the water. It'll look like that. It'll just be clear. You fill it to this little white line. And they'll place it in this meter we have. It's called a colorimeter, and it will read the chlorine value. So you have to put the blank in to get a background reading. You zero it. And then you'll add this reagent. It's called a GPD packet. And what will happen is, if there is chlorine present, there will be a color change. So did you guys see how that went from clear to pink? The more pink it is, that means the more chlorine is present. And we are required by the EPA to have chlorine in the distribution system. At minimum, we have to have 0.2 milligrams per liter. And at max, it's 2, is that correct? Yeah, about 2 milligrams per liter or parts per million. So this is reading 0.82, so well above the 0.2 limit. So that means it's good. It's killing any bacteria that would be present in the water. So speaking of bacteria, I'll show you another test that we do. Like I said, we have a sampler who their sole job is to go out to our different sample stations. We have about 90 throughout the city, and they'll collect a bacteria sample that will run here in the lab. And we use it, it's called MMO mug. And what we do is we add basically food to the sample bottle. You can see there's a little line right here. We fill it to the line. We add the reagent, we shake it up, we let it sit overnight, and then we come back in the morning to read them. And this is what a negative sample will look like. So it's got a little bit of a yellow tinge, but for the most part, it's pretty clear. And this is what a positive would look like. And what we're looking for in bacteria is for things like total coliform bacteria and E. coli. And maybe you guys have heard of E. coli before, but you definitely do not want that in your drinking water. It's present in poop. So it makes water pretty dirty. It's not healthy to drink, right? So you definitely don't want this in your drinking water. And so as you can see here, there's a color change. Just it going from this clear to yellow means it's total coliform positive, but we also want to see if there's E. coli present. So what we do for that is we have a black light that we shine on the sample. I'm gonna go hit the light. And if E. coli is present, it will glow. So can you guys see that a little bit? I know it's kind of hard to see, but it's fluorescing. So that means it's E. coli positive. And don't worry, these are ones we made in the lab. We purposely put E. coli in this so it would do that. All of our samples are negative and don't have any bacteria in them, or at least total coliform in them. So that's just one of the many tests that we do in our microbiology lab to make sure that the water is clean and safe to drink. And each month, our sampler, they have to go out and collect at least 120 samples. So that way we, throughout the month, can look at 120 different samples and say that they were all negative for bacteria. That's what we're required to do by the EPA. All right.
All right, back to the treatment process here. So again, coagulation was adding the chemicals. Flocculation is me stirring it. And what you're about to see is the sedimentation portion. And that's where all these particles that are clumped together, they're now heavier than water, and they're gonna fall out to the bottom. Again, this is sedimentation. Ooh. See how they're all kind of clumping up at the bottom there? Little dust tornado. So yeah, now that all the particles are clumped together and it has had time to disinfect, so this should be bacteria free, then you go ahead and you take it over to our man-made filter here. And we do filtration. So I know most of you probably said, well, I don't know that, but I would assume most of you said you probably wouldn't drink the initial sample, the dirty silty one. But you see here, all that stuff was settled out and now it's filtered out and it's disinfected. So this water is ready to drink. So, and that's kind of similar to what we do at the treatment plant, except instead of using a towel to filter, we use those rapid sand filters that you saw in the video. They use just basic specially spec'd sand and gravel to allow the water to trickle through. And then instead of a beaker, we use those that settling basin that Willie Water was trying to swim in. So, and then now Emily will show you another test we do in the lab. This is the alkalinity test.
Okay, so earlier I kind of showed you the microbiology side, looking at things like bacteria in the water, but now we're going to look at the chemistry side. So things we look for is pH. We test for total alkalinity, which that's a really big word, but it just is the ability of water to buffer an acid. And we also look at total hardness. And total hardness is made up of calcium and magnesium hardness. And that's really important because there's these really massive pipes that go from the treatment plant out to your homes. And you want a little bit of a film on the inside of those pipes to act as a protectant. So we want a little bit of calcium and magnesium to create some hardness as almost a protective lining in the pipes. Because maybe you guys have heard of Flint, Michigan, and they were without good quality drinking water there for a little bit. And that was because they changed their source water and it had a higher or a lower pH. It was too acidic and it ate away at the calcium and magnesium lining in their pipes, which then is what led to the leaching of lead and copper. So we always want to check the pH to make sure that the water is at least above an 8.3 normally. And then we want to check the alkalinity and the hardness to make sure that it's safe when it gets to your home. So I'm going to show you how we do that. We would take a sample from either our Ottawa or our Miami plant. We fill it in a volumetric flask, and I'm making a mess, but it's fine. You make a mess all the time. It's just water. All right, so I fill it up. This is a volumetric flask. I fill it to that little line. I want the meniscus right there. I'll put it in my Erlenmeyer flask. Hopefully you guys can see this. All right, so we're going to look at alkalinity. So I'm going to add some sodium thiosulfate. And what this does, it it just quenches the chlorine. Because if there's chlorine present, it can make our endpoint or the color change a little weird. I'm going to add our indicator here. And as you can see right now, it's like this really pretty blue, right? This aqua blue. But what's going to happen is when I add this acid, it's going to change colors. And when it changes colors, that will be my endpoint or my final value for the alkalinity. So hopefully you guys can see this. Starting to change a little bit. And now it went from that aqua blue to this really pretty red. And that means that is at endpoint. And that would give me my final value for my total alkalinity. So like I said, in the lab, you look for total alkalinity and total hardness when we do titrations. That's a big portion of our job during the day, is to just do a bunch of those titrations to test the drinking water. I think that's all we have to show you demonstration-wise, but hopefully this shows you guys that there really is a lot that goes on behind the scenes to make sure that your drinking water is safe. There's a lot of people, a lot of operators in the plants that are making sure your water is safe, and then us here in the lab are doing a lot to make sure that your water is safe. So no need to drink bottled water. The water that's coming out of your tap is good, especially if you live within the city limits or in Montgomery County.
One other thing I was going to mention, we do, for the teachers, we do normally do tours, field trips where you guys can come out and bring classes out here. Right now, obviously, with restrictions, we can't do that, but I'm sure those will be hopefully start to be lifted soon. So feel free to reach out if you guys are interested in doing some sort of tour with your students. So
I'm sure you guys have lots of questions, so ask away.
One class would like to know, what about Legionella? Do we check for that?
Excellent question. Excellent question. So we do not have the ability in our laboratory right now to test for that. And it was a big concern recently with COVID and buildings being abandoned or not being in use for a long time. And then people bringing people back into those buildings and not following proper flushing protocols. We could send out Legionella samples if we were interested or if we thought we had a concern, but right now it's not really an EPA required test, and it's typically, like I said, it happens when buildings are shut down for a long time and people don't understand there's a flushing protocol that you need to follow before you open that building back up. So it's not really an issue in fresh, clean drinking water.
What is your favorite part about your guys' jobs?
Yeah, for me, my favorite part is that every day is different. There's a lot that goes on here. We do a bunch of different testing. There's different events that may happen, like a main break or a tornado that can throw our plans out the window for the day. So like I said, the environment's always changing. You get to kind of do a bunch of different things. You get to do chemistry one day, you can do microbiology the other day. So I like that aspect of it, because I think if I sat at a desk all day just staring at a computer, I would go crazy. So I like that. And I also like that I feel like I'm making a difference. So I know that when I'm coming to work, what I'm doing matters. So I know that I'm creating a resource or helping protect a resource to make clean, safe drinking water, which is awesome. It's really important.
Yeah, same kind of thing as Emily. Every day is different. Before I was a supervisor, I used to get out a little more. It is nice to be able to go and be out in the field, but also do some lab work, but also do some desk work. It's a really good mix of all three of those things. Like I said, I don't get out as much as I used to. Same kind of thing with Emily, though. It's a feel-good job. So even when there is something that happens, like on a weekend or I have to work 16-hour shifts or something like that to remedy a problem, I don't go home feeling like, oh, I hate my job. I go home thinking like, okay, what I did was important. So I this is what I'm here for. I'm here to address these problems. So it makes you still don't feel bad even after working a long shift. So same kind of thing. Just I feel like every day I come in that I'm doing something important, and it's always different every day.
How much chlorine is usually needed to create a safe pool?
A A safe pool? I don't think it's as much as you think. I think, so we keep our water at about 1.5 milligrams per liter. If I'm not mistaken, a pool isn't much above 2 or 3. It's not really that high. It's not as high as you would think. They just have to maintain it. And Rachel, you may have more insight on this since you worked at a pool. I don't think it's very much higher than what we treat our water to.
Yeah, I think between 2 and 5. I don't think it's higher than 5.
Yeah.
But the chlorine smell isn't chlorine, so that's probably what is deceiving.
Yes.
It's called chloramines. It's from too much ammonia or urine sometimes. So it's the opposite of what you think.
How did you guys get into the water field?
Yeah, for me, I really didn't know this job existed, honestly. I was in college, so my major is in environmental health, and I thought I would go more the public health side of things rather than water. I really needed a second internship, and I saw on Sochi, which is a intern service basically, that there was an opening here at the water lab, and it said chemistry in the title, and I said, well, I'll apply for it, but I hated chemistry in college, so I don't know how that's going to work out. It's a few years later, and I'm still here. So I got lucky, and I was here right as a lot of people were leaving, retiring, and that's kind of, I ended up staying after I graduated college.
And I was always interested throughout college in water treatment and working in the water industry. When I first graduated, jobs were a little sparse in general, and a few times jobs did come up at different water facilities, and I did apply for them, but at the time I didn't have any experience. Then I went out to the field, and I got some experience working in labs for a few years. And then once I had that experience, I noticed a job opening at the city of Dayton working in their lab, and I applied, and I got there, fell in love with the job, and I've worked here for about 7 years now since I applied. So.
Do you need to test water sources like lakes and rivers around the water plant, or just the water within the pipes that lead to the water treatment plant?
So we actually, part of the sampler's job that I mentioned earlier, they go out and collect bacteria. We actually have another sampler who goes out into the well field. And so they'll collect wells. We have 2 different types. We have production wells. Production wells are actually what's used in production. So it's what is sent to the plant. And we have monitoring wells. And monitoring wells are, well, what we monitor. So we look at the chemistry of that. We'll look at things like volatile organic compounds. We'll look at the metals, salts, all that's present in the monitoring wells.
We kind of piggyback off of what environmental does. Environmental is more early warning. So they investigate new areas where there's possible new plumes or new issues. Whereas we have a set amount of monitoring wells that we know what's there, and we monitor it and make sure that it doesn't go up. And if it does start to go up, then we work with environmental to do further investigations.
Alrighty, I think that is all the questions, unless you guys have any other things you would like to share.
Yeah, kind of piggyback on what we said earlier about careers here. So the water industry, a lot of people got into the water industry at the time of the Clean Water Act, and a little bit after. The water industry really started booming and needed more employees. So a lot of people are actually retiring from the water industry. Most people that get into the water industry stay there for life. So that's one reason why there wasn't a lot of opportunity when I graduated college. But right now, there is really a lot of people retiring and leaving the water industry. And there's really a huge need for basically science-related people to get into the water industry. So if it is something you're interested in, I encourage you to look into that. Especially, I know it's a long time away, but always be thinking about your future. And if it is something you're interested in, look into maybe doing a science in college or something related. There are specific water industry related classes that you can take locally or in different colleges. So it's definitely a good job to get into. And it's something I don't think that'll ever be, knock on wood, replaced by any kind of automation or anything like that. It's always going to need humans hands-on doing the work and making sure everything's good. And it's kind of like everything. As time goes on, it's going to be more complex and need more people to do the work. So.
Thank you so much, Brandon and Emily, for teaching us about the water treatment process.
Thank you.
Thank you.
And thank you, everyone, for being here today. We hope we can see you tomorrow. Bye.